Hello, ladies and gentlemen, of the XAFS 2022 conference in Australia. I'm Andrea Di Cicco from the University of Camerino in Italy, and this work has been done in collaboration with Fabio Iesari, the Aichi Synchronization Center in Japan. We will be talking about advances in modeling X-ray absorption spectroscopy by Reverse Monte Carlo. And so the starting point is the expression for the XAFS structure factor, which includes integrals of the pair and higher order distribution functions, and you see J2 and G3 and G4 and so on, through signals which are related to the two body, three body, and four body distributions calculated by multiple scattering usually. And this is a ill-posed problem, but it's usually tackled by using a peak-fitting approach, which is based on the assumption of well-defined coordination shells, which works fine for crystals and molecules usually. Several alternative methods have been devised for different materials, especially for liquids classes. And in particular, the reverse Monte Carlo approach was pioneered by McGreevy in the last century, especially for diffraction, and can allow us to build the structural models, three-dimensional structural models compatible with experimental data. These have been successfully applied to X-ray absorption data by many authors, including us, as you see, and more recently by Timoshenko and Kuzmi for crystals. We had already very successful results for analyzing XAFS for simple molecular and liquid systems, for which we found important to combine diffraction and also computer simulation data for the medium range ordering, and we also take the problem of evaluating the dimensions and sample of atoms to be considered. This communication, we present some recent advances and applications, and you can find more details in our recent work on physics, chemistry, and chemical physics of 2022. So, very briefly, the reverse Monte Carlo technique is based on the Metropolis Monte Carlo algorithm, and the random variable is the difference between experimental and calculated signals for a defined energy point. We assume that there is a random distribution, so a Gaussian distribution, and the total probability is this product of distributions, so that we can build the chi-square function, which is a summation over the differences between calculated and experimental signals divided by the variance, so the noise of each experimental data. In this way, the total probability is proportional to the exponential function of chi-square divided by 2, which mimics the same behavior of the classic term energy potential divided by the temperature in Metropolis Monte Carlo. So we apply the same algorithm, and the advantage is that we have a model-independent technique for refining the various position of the atoms for the calculated signals, and we can refine different experimental data from different sources, and this is coded in a program which is called RMC GNXS. In this program, as I said, we can combine different data. So in particular, we can combine different experimental EXAFS data, multi-edge and for different atomic species, and then also adding partial distribution functions which can be derived by other techniques. For example, X-ray diffraction, neutron diffraction, molecular dynamics, and so on. We can apply the method that is briefly shown here, which is an iterative method, statistical methods, by using molecular replicas for molecules or periodic boundary condition for extended systems. Briefly, the application to molecular system can show us the accuracy of this approach. So, for example, this is on the left, you can see bromine, which is a molecule of only 2 atoms, and we can reconstruct easily the pair distribution functions of this molecule, which is in excellent agreement with current electron diffraction data, which are used for these molecular compounds. So, for example, on the right, you can see the refinement of germanium tetraiodide, which is a tetrahedral molecule. So it's a more complex molecule. So you can see 2 peaks of the pair distribution and the classic bond angle distribution as a tetrahedral angle. And this, so in this way, we can reconstruct with an ensemble of thousands of atoms, even more, average over many configurations, the local structure of these molecules. Just 2 words about the uncertainty on the parameters, which of course is affected by noise. So here we have done a test, but there are many that we can see in another talk of the last year and also in the paper. So we added artificially noise, and we can see that the values for the parameters that you can reconstruct deviate from the correct values for increasing noise. So you should have quite nice data to do that. For crystalline system, we can do the same approach with periodic boundary conditions. And what you see here is crystalline germanium, and on the left, we constrained the diamond structure with a model for the vibrational amplitudes. So we can arrive to a very good definition of the pair distribution function in this system consistent with our data. But if you include, if you don't include the constraint of the pair distribution function, you lose the correctness of the GOVAR at medium range order. So it is absolutely necessary to constrain at medium range and long range the structure. This is true also, for example, for another crystalline system, silver bromide, for which you can see, I mean, on the left, we constrain the structure, and you can have an excellent agreement with previous determination for crystalline silver bromide, while if you don't constrain the structure, you have larger fluctuations of the data, of the reconstruction, and also deviations from the correct behavior at a medium range. And for liquid and amorphous systems, which are probably the most interesting systems to be handled by X-ray absorption, because are disordered. And you can see that, again, we have a very important information that you can get from X-ray absorption at short range, but you absolutely need a constraint at medium range order, as you see, because otherwise the reconstructed GOVAR with only X-ray absorption data deviate significantly from the known result from X-ray diffraction, for example, for germanium in this case, and for silver bromide at high temperature. We see that you get some new information at very short range, which exceed the previous knowledge, and so we improved our knowledge about the liquid at short range. But of course, we need some constraint at the medium range. So in conclusion, the Reverse Monte Carlo approach has been applied to molecular crystalline disorder system, combining multiple EXAFS with results of other techniques, and allowed a detailed reconstruction of the structure. The combination with medium range order constraints, so partial pair distributions provided by other techniques, is shown to be an important condition for reliable reconstruction. Due to its unique short range sensitivity, the application of XAFS to disorder stiffness is particularly interesting and can provide important additional information. Of course, it's very powerful, but there are conditions: access to low noise, access experimental data, reasonably extended in K, and correct application of the algorithm, including the estimated noise. Thank you very much for your attention.